everyone. My name is Mugabe Samuel, and I'll be taking you through our paper, Interpretable Machine Learning to Solve Bicycle Imbalance in Bicycle Sharing. This paper was authored by Simon Onen and Mugabe Samuel, me. These are the contents of presentation, introduction of our paper, background and motivation, literature review, methodology, outliers, methodology continues, grouping the data set, results and discussions, explainable AI. Here we use the LIME method, conclusions and future works, acknowledgements and references. Allow me introduce bicycle sharing as a modern transportation option, that allows users to rent bicycles for short periods of time. Now, this bicycle sharing system it makes bicycles available at different locations for users to pick up and hire. And it's gaining popularity in most cities because it gives an alternative that is user-friendly, it is cheap, it is environment friendly, it helps lower the carbon emissions that come from the cars, and also it helps with the health, whereby people are able to break some sweat as compared to sitting in a car and then you're driven off. Now, the bicycle sharing system mainly consists of, bikes, of course, and then the docking stations at different locations, and also a platform for hiring. This platform could be a website, could be a mobile application, depending on the administrators of the bicycle sharing system, whatever they choose to use. Now, the bicycles start off the day at their respective docking stations, and users keep picking bicycles from docking station A to docking station B, docking station B to docking station C, and so on and so forth. Now, after some time, you realize that maybe bicycles at docking station A are less, but then the bicycles at docking station B are more than what is required there. Now, this problem is what we call bicycle imbalance, whereby you experience in the system an overflow of bicycles at certain docking stations and an underflow at other docking stations. Now, this problem has been disturbing most bicycle sharing systems, and the causes of that could be the location of that station, the population density around that docking station. If the population density around that docking station is high, of course, the bikes will get depleted very fast. And also the behaviors of the users. Users have different behaviors and preferences, could also affect. Before approaching our problem, we reviewed some papers. One of them was Zifeng Wang, whose paper described mainly regression models, trying to predict the number of bike users that will turn up. Then Zhu proposed a multi-block hybrid model, for helping to predict the bike demand. Lee gave us a study exploring multi-categorical probabilistic approach for bike usage, we also reviewed Young's paper, who was proposing a position method named PSA. Then Francisco's study, his mainly was around the COVID-19 pandemic and lockdown and how it affected urban mobility, especially in New York City, and how bike sharing and its relation to other forms of transport was affected by the lockdown. In our methodology, we got our dataset from Blue Bikes. There's a gentleman called Calvin. He helped us and gave us permission to use the dataset, their open dataset, and it was mainly for study purposes. Then we applied our explanatory data analysis. We cleaned the data. Lucky enough, we didn't find very many missing values and null values, so it was a bit easier that way. Then after cleaning our data sets, we also looked at the outliers. We're going to look at the outliers in the next page, but we looked at the outliers and knocked off some values. Then we got these um, from the features we had, we identified important features, which included, there was trip duration, start station ID, start station time, bike ID, and also the birth year. Now, from these important features, we managed to engineer new features, generating new features. For example, from the start station time, we engineered and picked out the month, the day of the week, the day of the month. From the start station time, we picked out those features. Of course, we first converted it into date time before picking out those values. Then after coming up with our new data set, we fed it into our models. We used linear regression, random forest, k-neighbors, support vector machine, and also gradient boosting. Mainly, we fitted there and made our predictions. And on these predictions, we were able to evaluate the performance of our models. Of course, for the performance metrics, we looked at mean, average, error, MSE, mean squared error, and also the R2 score to evaluate the performance of our models. We also split our data set into training and validation. Then in the training, that's where we split the train test, but we had to split off a part of validation. Now for the outliers, we used the interquartile range, whereby we applied IQRR, and it gave us the lower bound and upper bound. And for the feature of birth year, we knocked off values of 1952, they're about, though they could have affected our model maybe negatively. So we knocked off those values and remained with something that is very useful. We also had outliers in trip duration. We also applied interquartile range and knocked off some values, the outliers, and remained with what you are seeing on the right here. And we went ahead and applied the correlation, came up with this correlation heat map, whereby, features are considered to be highly correlated if they have a correlation of 0.9 and above. Those are very correlated and therefore might affect the model the same, might have the same effect on the model. After grouping our data set and feature engineering and coming up with this new data set, we came up with, before that, we made an assumption that if a bike left a station and came back to that station within 1 hour, we knocked out those values because we considered that such a value did not cause an imbalance since the bike left and came back within the same hour. We made that assumption. Now, in our new data set, these are the features that we had: start station ID, start trip of the week, start trip day, average user age. We came up with the average of users at that station, average trip duration, average of the trip duration of users at that station, and number of trips, and then the number of bikes. Now, the number of bikes is what we are trying to predict. So this will be our Y value when we are fitting into the model. We fed it into the model and it gave us these values, for the KNN. That was the when we applied cross validation to the KNN. Cross validation mainly it splits into tests, train test, but this time the testing set, it keeps on shifting. The testing set today is A, and then the next time the testing set is B, testing set is C, and then the rest is training. That's what the cross validation mainly was giving us. Then also for the these other models, for example, linear regression, those we got the metrics and we got the errors, and also the autoscore, which mainly shows the variance of the dependent variable and how predictable it is from an independent variable, mainly the R2 score. And then yeah, the results tallied like that for random forest and also support vector machine and also GBR. For our explainable AI, it's mainly, we used LAME, but these are mainly, when someone says explainable AI, they're talking about, methods that, allow maybe human users to understand why a model predicts such way, why a model gives such results, given its algorithms. It's better than the black box model where you just feed in data and then it predicts for you without an everyday user knowing why it predicted. So now we used LAME, which is local interpretable model agonistic explanations. It zooms in into a data point and tries to analyze why the model predicted the results that way. And as you can see, LAME explainable for linear regression, it was showing us that the features of number of customer, gender unknown, our data set had 3 genders. It had male, female, and also unknown, and also number of gender. This is for the female gender, and start trip month. These were positively affecting our model, and then the others in blue were negatively affecting our model. Then the same LAME was applied for random forest, and as you can see, number of customer, gender unknown, number of gender female still appears, start station ID, start trip day of month, and start trip month positively affect the model. We would like to conclude, by saying that for our problem, regression models were what we used because, we were trying to predict continuous values, which are the number of bikes at docking stations. Using our model, bike sharing system administrators can use it to accurately predict bicycles at their different docking stations. And then in our future works, we did all our works without considering the time series component in our data set. And maybe now for the future works, next time we will consider the time series in our future works. Acknowledgement mainly goes out to Aurelian Calvley, the one of Blue Bikes, that gentleman. We sent him emails and he responded instantly, gave us permission to use their data set for study purposes. Then also City Bikes, they also helped us in a way. So we have to acknowledge them. And these were our references. Yeah, thank you. Thank you so much for listening.